for the organizers, for the opportunity. And so I'm gonna talk about a joint work with a couple of guys here. Maybe you know some of them. And I will start with a short introduction to Bell scenarios. So I'm kind of already assuming that there is a source here, a quantum source sending quantum systems to Alice and Bob. And Alice will select a measurement to perform in this quantum system and get the result of this measurement. Bob do the same, and the statistics will be given by Born's rule, where rho here is the state that they share. And maybe the main question on this subject is to know if these quantum statistics can be decomposed in a model like this one here that you call by a local hidden variable model. But what I'm really interested in the transfer this model that starts with the statistics to the states. So now I have a definition here, what is called by a local state or LHV state. It is a state that for all choice of measurements in Alice, all choice of measurements in Bob, the statistics that you can get can be decomposed in a local hidden variable model. And if this is not the case, the state is non-local. So maybe you are more familiar with this definition here, that a state is non-local if it can violate a Bell inequality. If, on the other hand, if a state does not violate any Bell inequality in any scenario, the state is local. Okay. So, giving some examples, everyone here knows that separable states are local states. They do not violate any Bell inequality. On the other hand, all pure entangled states violate CHS8, so they are non-local states, non-LHV states. But for mixed states, it's not that easy. There are differences between locality and entanglement. Here I have a kind of pictorial representation of the set of quantum states. In this gray area here, I have the separable ones. Everything that is outside this area are the entangles. And for instance, you can have some guys here that are local but are entangled. So someone here, it's local but entangled. And a good way to visualize it is based on this family of states, the Verne states, which are just this convex combination between the maximally entangled state and the maximally mixed state. And Werner have proved that for this parameter here, the parameter here that called visibility, when it's equal to 1/3, you have the transition between separability and entanglement. So it's the guy exactly in the border there. When the parameter is bigger than 1/3, you have entanglement. When it's small, you have separable states. And he also has proved that, for instance, when this parameter is 1/2, this state is local. Although it's entangled, it's local. Okay. So short introduction. And one possible question is, what more these LHV models would need in order to explain these correlations? As you have seen, you can violate the inequality, so it's not always that you have a model for the states, and you can ask what you could add. And there are many ways to approach this question, and maybe the most famous way is to add classical communication to the scenario. So I'm going to consider now a model which is not just the usual LHV model, but I'm relaxing the hypothesis and I'm letting Alice to send a classical message to Bob. So over this hypothesis here, I need to change what it is my model, my mathematical model, and it's basically adding the C here, which is representing the message that Alice is sending to Bob. And there is a similar result on it made by Turner and Bacon, where they have proved that in order to simulate all correlations for maximally entangled 2-qubit states, one bit, one classical bit, it's necessary sufficient. So you don't need to send a lot of communications in order to explain all quantum correlations, all quantum statistics that you can get with maximally entangled 2-qubit states. And for other states, they also have results. 2 classical bits are sufficient, but let's focus on this one. And this is also only true for projected measurements. There are some improvements on it later on. Okay, so now based on these new results, we got back to our diagram here of the set of states, entangled states. And let's say that this eta star is now the point in the transition between local and non-local. And so then for this guy here, you don't need communication at all to explain it with a local hidden variable model by definition somehow. On the other hand, the maximally entangled state, which is the variant state with visibility 1, you need 1 bit of communication based on Bacon's tonal results. And if I want to know, for instance, a guy here which is close to the border, and if I want to know how much communication do I need to explain it, I mean, that is not half of a bit, so I think you need to change the way that you quantify it, but you can talk about average communication. So in how much, I mean, you do communication some rounds and at the end you take the average. And it's easy to see that since this guy here is kind of combination of this and this, if it is some of the time you kind of do a model for this one, some of the other times you do the model for this one, it works. And in the average, the amount of communication that you need to explain a guy like this goes to 0 if you are approaching the border of the local and non-local states. Okay. So still a review, and that what you are interesting is more like in a different type of restriction on the type of communication. More especially, or propose you allow only communication of Alice outcome. So the A, what Alice get, and the result of her labs, he send it to Bob. So then you have something like this. Here is the scenario where, like usual Bell scenario, where Alice is sending, broadcasting her output to Bob, and Bob can use it to improve the model, the model that they want to explain. So it's similar to the Bacon and Dorner approach, but you restrict the type of communication that Alice can send. And again, you can want to know if you can explain more quantum correlations or quantum statistics. And okay, and you might ask, how powerful is this new model? Is it the same as the LHV, or is it more powerful, super powerful? And indeed, for sure, it's at least as powerful as the LHV model, right? That will give you more opportunity here to Bob to create the distribution here. And but it's for sure at some scenarios, for instance, in the CHS8 scenario, it's quite powerful. Indeed, you can simulate all non-signaling behaviors in the CHS8 scenario if you give this advantage here to Bob, if you let him know Alice output. So some case this model is quite powerful, but in general it's not it do not trivialize it. It's like there are some quantum behaviors that you cannot be simulate even in this model here if you go to more general scenarios. There's a paper, for instance, by Rafael Chaves. Okay, so nice. This is good, right? You don't want to have a model that is too powerful, then you can explain all quantum states. This is not the point, but you also want a model that is more powerful than the LHV model. Okay, and so first the introduction of the model, the models for the statistics, and you can again transform this model to the states to define what would be LTV plus out states. And the definition is basically the same as before, the same as the local states. You just change your model here. So a state rho is LTV plus out if for our choice of measurements here of Alice and Bob, doesn't matter in what scenario you are, what is the number of measurements, the number of outputs. For all of them, when you go to the quantity statistics here, you need to have explanation for it using this new type of model, the model where you allow the communication of the output of Alice to Bob. If this is not the case again, then my state is non-LTV plus out. Okay. And so I'm already ready to state our main results. And our main result says that, at least for projective measurements, a qubit in Alice, qubit in Bob. So a qubit state is LHV plus out, if and only if is LHV. So what I'm saying here is that if I want to explain, let's say if I start with a state rho and I want to explain all the correlations that I can get from this state, all the statistics, if I can explain it with a LHV plus out model, I'll be able to explain it with a LHV model as well. Even though in principle this model is more powerful, when you go to states, when you go to all, to be honest, when you go to all scenarios that you can have with this fixed state, these two models are kind of equivalent somehow. And just rephrasing it, so outcome signaling is useless for improving LHV models for qubit states. And so the question is this unexpected? For me, it was, and I'm try to convince a little bit you guys that it is. And just using the example that I was constructing before. So again, this pictorial representation of the set of states. And if you remember, no, sorry, what you just, the result is just saying that these two guys are the same. So the LHV states or the local states are equal to the set of LHV plus out states, where this one here, you allow Alice to send her outcome to Bob. And if you remember, if I just focus here on the family of variance states, and if you remember, if I want to give a model for a guy here, which is really close to the border between local and non-local, the amount of communication on average is quite small. It's going to 0. But if I restrict the type of communication to just be the outcome, and here you don't put any constraint the amount of communication, it's more in the type of communication. But if I do this restriction here, I will not be able to explain the correlations of this guy, even though the amount of communication is quite small, it's going to 0. So for me, it's kind of somehow unexpected. I would expect that this set here is a bit bigger than the LHV one. Okay. And I would like to give a sketch of the proof, just because there is a theorem there that I think is interesting on its own. And just to remember that the result, the statement is this: for projective measurements, a qubit on Alice, qubit on Bob, state is LHV plus out, if and only if is LHV. One part of it is trivial because, I mean, this model here is more powerful than this one. So if a state has a LHV model, a local model, for sure it will also have LHV plus out model. The other direction is less trivial. And how can you prove it? And it's basically, the proof follows from this theorem here. And it's more about, not so much about the states, more about statistics. And it says that if P of AB given X, Y, so the behavior, I have some assumptions on it. First one, it's non-signaling. Okay, it's good. Other one is dichotomic analysis. So the A here, it's just it's only +1 or -1. You don't just have these two possibilities, but it's okay as well. a lot of Bell tests are in this type of configuration. And now the assumptions, let's suppose that this behavior admits a LHV plus out model. And another one, and maybe the key one, is that there exists an input X such that the margin of Alice here is deterministic. So it's 0 or 1, only just two possible. Then over these assumptions, the behavior, the complete behavior will also admit a LHV model. So I start with LHV plus out and some assumptions here, end up with LHV model. Based on it, it's easy to prove the results. So we start with a state which does have LHV plus out model, and as in Alice you only have qubits, you don't lose any generality. If you consider only dichotomic measurements, you can prove it. So then you start with a generic set of projective dichotomic measurements, and then you add a deterministic measurement to it. The deterministic measurement will be something like this, identity and 0. And based on this theorem, for this new set of measurements, it will satisfy all the hypotheses here. Since this is the deterministic measurement, for this measurement, Alice marginal will be deterministic for sure. Then for using the theorem, you know that you have a LHV model for the statistics. So you have a LHV model for this state and this bigger set of measurements. And as this set is generic, it doesn't matter. So you are proving your result. So the state here will be LHV as well. So the idea of the proof. Okay. And one question that you have when you get to it was that, do you really need these deterministic measurements? Because in Bell scenarios, usually it's useless, this type of measurements, you don't have any advantage. And so you are curious to know if it is just a technicality of the proof, or if it is indeed something that you need. And unfortunately, you didn't find an answer to it. You could not disprove that is not necessary, or I don't know, find a different proof. But what you could find, which is also different from Bell scenarios, is that although it's true that these two sets are equal in general, but if you restrict the type of measurements that Alice have, especially if you restrict Alice measurements just to half of the block sphere, then there are some difference between local and LHV and LHV plus out models. So you have some non-local variant states that do admit LHV plus out model. And this is also not true in Bell scenarios. You can consider just half of the block sphere, and with it you can construct the whole model. So there's also a difference here. And you believe that these have a connection with the hypothesis before. Maybe you do not need to use the identity, but I don't know. Okay. And as I told, this theorem here, I think it's interesting by its own, and especially because you can kind of get a consequence of it, but I need to think a little bit more about it. But when I read this theorem here, I think you can get the same conclusion here. So if I start with any Bell test, especially Bell tests where Alice have dichotomic measurements, so any Bell test like this, which is against LHV models, I want to test if I do have LHV models or not. And if I violate these LHV models, based on this theorem here, I could extend this test to a text that will also be against the LHV plus out model. To do that, you just need to simply add in a deterministic measurement. But to be honest, you don't need to perform this measurement on the lab, because, I mean, if you do it, probably you get some noise, and then you will not get satisfied this hypothesis here. But you are in the lab, so suppose you select this measurement here. You just say, okay, I need to do this measurement, but I don't need exactly to perform it in the state. I can just say, okay, all the rounds that I do these measurements, I will give as output. The output corresponds to the identity here. So you are not exactly doing this measurement on the lab. So you are just kind of doing some processing, but based on this theorem, you now have some conclusions that goes even stronger than the usual one that LHV. You are going to the LHV plus out, which is kind of a relaxation. And I think it's curious, but I don't know if you can apply it somehow in some protocols. But yeah. So there is also an open question that approved was for qubit analysis. And it would be also interesting to know if this is true for any other type of states or general states, qubits in both sides, or if this is a property of qubit states analysis. I think it is, because qubits are quite special, but you couldn't find a way to prove it. And to finish, so the first thing that you see here that this is the similar result of Bacon and Toner. So 1 bit of general communication is already enough to explain, to simulate any statistics in 2 qubits maximum entangled states. And what you see in this work was that outcome communication is useless for simulating correlations for this type of states. However, if you restrict the type of measurements to be just half of the Bloch sphere, then you have a difference. And the final one is that any dichotomic Bell test that rules out the LHV model can also be extended to rules out the LHV plus out model by simply adding a deterministic measurement, which could be easily performed. Okay, so thank you. That's it.
Okay, thank you for the talk. We have plenty of time for questions. Anyone?
Thank you for the talk. It was very good. So I think I have maybe one clarification question and one question.
Mm-hmm.
You said that in your proof, one of the assumptions was that this P for a specific X was deterministic.
Yes.
So is this related to your assumption that the measurements are projective measurements or not? Like, is the statement that LHV plus out is the same as LHV when you have projective measurements, that is true, or that is true given an assumption? That's the question.
I think this theorem here is kind of apart from states and it's more about the statistics. But then for the results, indeed, it's important to have projective measurements, okay, because you can, I mean, you can't, if you only consider projective measurements, you can't, without loss of, I mean, you can satisfy these hypotheses here that they are dichotomic. It could be more, but doesn't matter if you are restricted to projective measurement. Okay?
Okay. My other question is that I've thought before, like, I mean, about this thing of if outcome communication would explain the violation of Bell inequalities and like Bell's theorem. But the reason I always thought for this to not work was the fact that the instrumental scenario also has a separation between quantum and classical. So if you had communication between A and B, then you could, and you say, this is the explanation. Like, I saw in the lab, I made a Bell experiment, saw that there was a violation, and then my explanation is that there's communication between, like, there's an arrow between A and B. But then if I go to the lab and I do the same experiment with an arrow between B and the quantum system, then I get more distributions that were not there originally because of the quantum classical gap of the instrumental scenario. So are your results related to this way of thinking at all? Like, it seems to me that it's a different justification, or is it related?
Yeah, I think it is a bit, but I mean, our results goes kind of against it because you are just realize that LHV and the LHV plus the outcome communication gives to you the same, right? But But what we want to talk is more about the states, not about the statistics.
Yeah.
So,
yeah, I don't think it's against it, because in what I'm saying,
yeah, it's not
is
against
you
it,
have
yeah.
both things. You have the quantum source and the classical
Yeah.
communication.
Yeah.
Yeah. Okay. Yeah, we can talk later. Cool.
Sure.
Further questions?
So I am wondering, maybe to put it a bit provocatively, I wonder, is this result almost an accident? Because if I have POVMs,
Mm-hmm.
this cannot be true, no? Because I could copy my input. Say I have CHSH, right? I could copy the input into the output and communicate the whole thing.
Mm-hmm.
But I'm not allowed because the assumption is projective measurements.
I think it's maybe not. This is not the point, I guess, because I think the problem is that it's more like if you have a lot of measurements, you cannot copy it. In CHSH, for sure, you could, because you just have two. And I think you can indeed copy it. It doesn't matter too much if it's POVM or not. But the point is that if you have several measurements, then you just need to send, for instance, a bit to Bob, and then you cannot know what was the input X. You could separate in two classes, but this will not be enough to you.
So if I was allowed POVMs on 2 qubits,
Okay.
I would have one output, which is the output I would have from the projective part,
Mm-hmm.
and the second one would be just a piece of my input.
Yes.
Like the input. And then I send the whole thing, and then you have knowledge of your input on Bob's end,
Uh-huh.
and then you can do anything.
Indeed.
So wouldn't that... Yes, but you could clone an infinite string, no, of inputs into the output. That's a given that it has to be.
Yeah, it depends on which scenario you are. That's if you are, I don't know, if it's 10 measurements and 2 outputs, then you cannot.
So you have to assume the output cardinality in the.
To be honest, you don't need, because if you restrict to, maybe you are right, but if you restrict to projective, doesn't matter if are 10 outputs or 2, because you could simulate these projective measurements on qubits. They are kind of trivial, right? The other outputs will be 0 somehow. So yeah.
Yeah, indeed. So what I'm wondering is really whether projectivity is there to prevent a useful cloning of the input to the output. Uh-huh. I will ask you more later.
Okay, thank you.
One more quick question. If not, so let's thank Carlos again.